Okay, we were discussing about bulk modulus of elasticity K, which is given by ratio of change in pressure to the volumetric strain dV by V, and compressibility is the reciprocal of that bulk modulus of elasticity, which is given by 1 by K, or you can write it as volumetric strain dV by V to the dP ratio, change in pressure ratio. Next, one more problem we'll take for the homework. You can write down, or we just understand what is this problem. Anyhow, you have the notes with you. You can refer this question and again solve it as a homework. Here, they are asking to find the pressure that must be applied to water. See now, again the question is, can you pressurize the water to reduce the volume? Is the question. So find the pressure that must be applied to water or on the water at atmospheric pressure. Means initially it is atmospheric pressure. Now how much extra pressure you have to add so that it will reduce its volume by 1%. Take K equal to 2 gigapascal. So again it is the question of how we write dV by V, change in volume to the original volume. So how much I have to write there? dV by V for this problem. For 1% volume reduction, how much to take for dV by V? Yes, 1 by 100, correct. So that will show us how much is the 1% reduction in the volume, or it is nothing but the, yes, dV equal to 0.01 V. Very good. So with respect to equation, if you want to write, you can write it as dV equal to, as in last problem, 1 by 500 parts, what we got confused. Here you can write it as percentage to some value in decimal or in parts, 1 by 100th part, or you can write it as dV is 0.01 of total volume, capital V. So like this you can consider and you can try to solve this problem. And here they are telling take the bulk modulus of elasticity K value as 2 gigapascal. Okay, if anyone has solved it, you can tell the answer, or later also you can solve it. Anyhow, I told it for homework. Answer is also given there, but you can just try and check the answer whether it is correct or not. So to understand, for this much of bulk modulus or the uh, given bulk modulus of elasticity 2 gigapascal and 1% of volume of water to reduce, the pressure what is required is 20 megapascal, 20 into 10 to 6. So much of pressure we have to apply. Then only 1% of volume reduction will be there for the water. So there will be small change in reduction in the volume for the incompressible liquids also. But the range of pressure or the force required is very high. I hope you are understanding. Okay. Not continuously changing volume like gases or air if you take, just by applying small forces by our fingertips, fingertips, very small forces, I can compress or expand the air or the gas. But same thing is not possible for the liquids or the oil. It is having very high or a very less compressibility, which requires very high pressure difference or the force difference to overcome very small amount of change in the volume. That is our understanding here. Okay, we'll move to the next point now. The next concept is surface tension. So as one of the students asked the doubt whether before applying the force tangentially or from the upward direction, what may be the condition of that plate. So as we were discussing only the condition of a plate or a small thin surface of negligible thickness, here the property of the liquid which is resistancing it to submerge or fall inside the liquid is the surface tension property. Or you can also take the example of, as I told, a hollow cup or a small plate in your home. The meal plates also you can take. Empty meal plate you can take. Just keep above the surface of water in a tank or in a container where water is stored. Just to keep that plate above that water surface. It will float. Yes or no? So that floating is possible because of the surface tension. So this surface tension property is nothing but whenever the liquids have more cohesive forces, the bonding between the molecules between the same liquid particles, if it is more, then the surface tension is also more. Okay. And it should have less adhesive force. Adhesive force is what? The bonding between the molecules of the liquid and to the other molecules. Say, for example, water I will throw on the land, on the surface or on the skin, it will stick to the surface. Why? Because it may be having, I'm not telling it is having less adhesive force. It may be having relatively less adhesive force or more adhesive force so that it is sticking to the surface. If you take the paint or something, it will stick to the surface. After very less time, we cannot remove it easily. That is the surface tension property. So this all depends on the adhesive and cohesive forces. If the cohesive forces are very high, means surface tension will be very high, so that we cannot separate the molecules of the same fluid easily. This is one condition. One more thing is the adhesive forces of the high surface tension liquids will be very less or very low. Means they cannot stick to the one other surface. Say, for example, if you take the mercury or some liquids, even though if you fall it on the surface, like on desk or on the floor or on the skin, it will just slide down to the surface, or it will just slide. It will not stick to the surface. You might have seen such liquids like mercury or some examples you may take, or some leaves outside you might have seen. Whenever the rain starts, the liquid droplets on the leaf, it will just fall on the surface of that leaf, particular leaf, and it will roll like a ball without sticking to the surface of that leaf. Means what? Adhesive force or the bonding, the possible bonding between the different molecules of the different substances is very less. But the bonding force between the same molecules is very high. That is what I want to try to convince you. Have you understood adhesive and cohesive forces? Or you may also recall the type of bonds or the gum you may get in market. They will ask for, do you want for adhesive type of bonding, or do you want the cohesive bond? So normally all the different gums or the sticking materials are made up of with the more adhesive forces, because it has to stick with different types of materials. There we need more adhesive force, but in this we need more cohesive force for the surface tension. The point is clear? All are attentive to the class?
Yes, sir.
Khalid,
Yes, sir.
are you understanding what I'm explaining? All are convincing? Okay, thank you. Next question. So in the sketch, what they are trying to explain you is, in a given container of any liquid, to consider any molecule or a uh, droplet of the given liquid, it will be surrounded by the cohesive forces. All these cohesive forces are trying to attract other molecules, each other, of the same material. And as they come, or as they are near to the surface, or whichever the molecules are near to the surface, see this, one of the surface is shown with the hemispherical body. You can observe the cohesive forces which are attracting with the other molecules are acting downside. So whenever the cohesive force is more, so molecules with the inside this bubble also they may attract each other, or outside this surface what I have considered, whatever the molecules are trying to come near to that, these will be attracting to each other. And whatever the surface is in contact with air, it is not having any attractive force because adhesive forces are very less. So comparatively with other liquids, if you talk, some of the liquids will have less adhesive force relatively. Some of the liquids will have the more adhesive force. So generally, if you talk about more of the liquid materials will have more cohesive force than the adhesive forces. So due to that, what happens at the surface? If you see half hemispherical, this is acting with the cohesive forces of the other molecules which are trying to attract it downside. And inside also, if you see inside this hemispherical body, if you see the different molecules, those are also trying to attract each other and trying to remain in the liquid itself. They are not trying to attracted by the air, or they are not acting with the air, or they are not trying to uh, bond with the other surface. Okay. So in this situation, what will happen? There is a thin film is generated at the surface where it can sustain some load. Okay, like if I keep one empty plate here, it can sustain the load. I can take the metal hollow cup. I can just slowly keep on the surface of this surface tension. It can float, even though the density of the metal is more than the water or any liquid. It will float for some time. But once it is filled with water itself, or once it is filled with the some mass of any fluid or solid material, it may submerge inside. Or if we apply the force which is more than the surface tension, then it can submerge inside, and due to the heavy density or more than the surface tension force, it may come to the downside surface. Okay, so this surface, what it can sustain some load, or the property of the liquid at the surface offers some resistance against the tension, is called as surface tension. By the word itself, you can remember the definition. That is, the tension developed by the liquid surface or at the surface to resist some external forces is called as surface tension. So that is denoted by sigma here in the bracket. So what will happen? What are the effects of this surface tension? It can support some load, small loads it can support, or because of the surface tension property, it can form some droplets, bubbles, or cylindrical jets. So as I can take an example of droplets, say for example, from the tap, if you try to slightly open it, the water from the tap, slowly it will fall down in the form of droplets, drop by drop, it will fall. Why it is falling in the form of droplet in spherical form? Because it is having more tensile force or the surface tension forces. All the molecules of that water are trying to be in a spherical form or be in contact with each other. They're not trying to sprinkle out or not trying to attract to the atmosphere more. So due to this, what will happen? Whenever it is flowing in a droplet form, due to the surface tension itself, it is having some form of the liquid in spherical form or in any other curvilinear or the curvature form, but the molecules are not trying to go away until and unless we are trying to overcome that surface tension. Once it falls on the ground or on the any surfaces, it will try to spread out, because at the given point the surface tension might have lost, or we are trying to take it out from the surface tension forces. So in such cases, it will flood outside the surfaces. And bubbles, if you see, this also we have discussed in the early classes. Say for example, take a bucket of water itself, and in that you try to open the tap with high pressure of water and see the mixing of that water and phenomena, what is taking place in the bucket with high pressurized water falling on the some part of water which is stagnant earlier. Now once I tap open complete the tap with high pressure of water, what will happen? Suddenly it will start mixing with the water molecules. At the surface, it will try to form some bubbles. Suddenly the bubbles will come out and they will burst out. Have you seen the phenomena? So this bursting of the bubbles, if you see, the bubbles are made up of inside air and outside air. And just one spherical surface or a ball-like surface, only the surface is formed by the liquid. Or also you can consider the soap bubbles. Easily you can form the bubbles there. What will happen? For some time it will be there on the surface. After some time it will burst out. So this bursting is possible when there is a pressure difference between inside air of the bubble and outside air. If there is no balance between both the pressures, then what will happen? The bursting of the bubble of air will take place until it will overcome the surface tension of that liquid surface, which is the hollow surface which is prepared by either water or by the soap with water mixture. The point is clear to everyone? Okay. Now coming to the last one, cylindrical jet form means we are taking just standard forms of the liquid where you can analyze the surface tension. There may be any other non symmetric or not a standard geometry. It may be also forming in any other form also. Okay, cylindrical jet where it may be formed cylindrical type of volume of the water or any liquid where you can see this cylindrical type of volume. Any examples? Water or liquid in cylindrical form. It may be completely filled with cylindrical form or it may be half cylindrical form where you can observe water tanks. Water tanks are square type or rectangular type. Cylindrical type. Yes, water tubes. Very good. Anish Chaudhary and Varsha. They are telling that water tubes or pipes you can see. Yes, very good. In well. Yes, correct. When water is stagnant, in well, if you see, it is in vertical cylinder. In pipe, horizontal pipe, if you see, it is a horizontal cylindrical form. So whenever the pipe is halfly filled, you can take it as half cylinder, or if it is completely filled, I can consider it as a cylinder jet of water in the cylindrical form. So that water flow inside the cylinder, if we consider, I can call it a cylindrical type of or cylindrical formation. Now we'll analyze how to find out these all surface tension from the different forms of the liquid geometries. So before that, what is the relation between the surface tension and different elements? If you see, surface tension is having the units of Newton per meter, or it is a ratio of force to the length, force to the length, where the length is in contact with the liquid, or that length you can consider it as for any given surface, like plate, if you see the length of contact, I'm talking length of contact, not the area. The length of the contact, if you see, that length becomes the diameter for the plate. If I take a small blade of the small sheet of the metal which is floating on the water, for that I can consider the length of contact is the total length of the sheet itself. Okay, so like this we are taking the effective length of the given object which is in contact with the surface of the given liquid, that we are calling it as length L. Okay, so the surface tension is the force per unit length. So any layer or any line of contact of the surface, if you see that length of contact and how much force the surface of the liquid is applying on that plate or on the given surface or on the hollow body, that force we are taking F. So the unit is how much? FIL is Newton per meter. And from this also we can find the force. See, this force is not the viscosity force we are finding here. We are finding with respect to surface tension. So force I can find out by sigma into L. Or length also I can find out by sigma. Now we'll take first condition. First condition is the droplet. So in the droplet, if you see, the inside pressure and the outside pressure. So outside pressure, anyhow, we know that it's atmospheric pressure as per our concept. Inside pressure, if you see, the water molecules are connected each other. So as I told, water molecule as an example we are taking. It's not only water, it may be paint or it may be any gum or it may be any jelly-like material which is having high cohesive forces, or can take any other liquids also as an example, like oil also you can take. So in that droplet, we have inside this hemicircle or the hemispherical body, entirely it is filled with the same molecules of the liquid itself or the fluid itself. Only outside it is having air. Now, what is the surface tension which is built from this droplet? Because to overcome to just what I'm telling is to disturb this water droplet or to uh, cut this water droplet into two halves. What is the force required? That we are finding. That force is equal to surface tension itself. So how much is the surface tension is acting for a given length of that ring or the given length, if you see, that force required to overcome or to cut this sphere into two halves, that is nothing but force due to pressure required or force due to the surface tension, both will be same. So minimum force required to overcome this surface tension force, that I can call it as surface tensile force or the minimum force, or the how much pressure is required to overcome this cohesive forces of the given liquid body. So to understand that, here on the right side we have taken one half, cut half of the spherical object, droplet of any liquid. Now if you see, before cutting it, before taking the section, it is acting by the some surface tension force with the other liquids of the other hemispherical body. So assume it is a complete spherical body inside which we are trying to separate it. One part of the hemispherical on left side, one half of the spherical surface on the right side. So once you try this, before this, there was some surface tension acting on the surface of this droplet or the circular surface. So that is shown on by the arrow marks. Okay, and what is the pressure inside this droplets, which is trying to keep those all liquids inside the droplet, is shown by the pressure. So as I told you, under equilibrium of this hemispherical body, if you see for the droplet, I can write like this: the force due to pressure, what is applied externally, is equal to the tensile forces in opposite direction. I hope the point is clear. To keep this hemispherical body or to just the minimum pressure or the force required to separate this spherical body into two halves is nothing but equal to tensile forces or the surface tensile forces in the opposite direction. So if I consider the pressure force on the surface, I can write it as the pressure is applied on this circular surface to overcome that tensile force, maybe pi by 4 d square, because the projected area of this circle, if you see, the projected area is nothing but pi by 4 d square. or you can see here. If I have shown in the PPT, as can you see here on the top picture, a hemispherical droplet is taken. The projected area of this circle is pi by 4 d square, a circular area. On that area, this pressure is acting. So, pressure on one side, P into pi by 4 d square, to separate them half is should be overcoming this tensile force. Where the tensile force is acting? Tensile force is acting on the complete entire surface itself. But we are taking the line of contact. The line of contact between two droplets or the two hemispherical droplets is this ring, what is shown in the opposite direction of the pressure. That ring, on the surface or the line of this ring, the tensile forces are acting. That area we have taken pi d, not area, the length of the ring. If you see, it is the perimeter of that ring, pi d. So from this one can find out sigma, or what is the pressure required to overcome the surface tension for the given droplet. That if you substitute and find out, so P equal to pi by 4 d square on the left side, sigma is on the right side. If I divide this left side equation by pi d, I may get sigma equal to some form, or I can take this area of the projected surface on the right side and I can find out the pressure. So here pressure, minimum pressure required to disturb that surface tension of the droplet is around 4 times sigma by d. So it is inversely proportional to diameter, directly proportional to surface tension. Means as diameter of the droplet increases, pressure required to separate them is less, or as the surface tension is more for the different liquids, pressure required is also more to separate them. So as per the surface area and the line of contact, I hope you have understood the relation between the pressure and surface tension. Or also I can write surface tension sigma equal to d into p, okay, diameter of the given surface into pressure applied divided by 4. Any type of form you can use. This concept is clear? Okay. Yes. Thank you. Next, as I told you, surface tension for the hollow bubble, as I explained you can assume it in two forms. First form, I told you, take an example of liquid. As in daily life we see water. Take the spherical bubble of water itself and assume inside it is hollow, outside also it is filled with atmospheric air. And inside, if it is hollow, means it is not filled by vacuum or it is not filled by any other liquids. Yes, it may be filled with air only if it is hollow. Now what will happen? To balance this surface tension or this, to keep this bubble for some time. Up to what time? Up to the time where inside pressure of the air and outside pressure of the air, if they are equal throughout the spherical surface, if both the pressures inside and outside it is same, the bubble up to that time it will be retained. It will be flying in the air happily. Once the pressure inside the air or outside may not be possible because outside we have always atmospheric pressure only. That will not change suddenly. Okay, but the inside pressure of that air, if suddenly, if it is, see for example, bubbles will not be in the same constant area. That is one thing. For a given time, it may be constant. But as you see the bubble movement, from lower surface or from the water surface to the above with the or with the soap material. When it is flowing upwards, the volume of the bubble will be slowly increasing. Then it will burst. Why? Because the inside pressure of the air will be slowly increasing. That's why after moving some or flying in the air after some time, the pressure of the air what is built, which can overcome the surface tension, it will go up and burst. One more example is, take the water is mixed with soap or the detergent or some shampoo. There, the bubble formation is very easy for us. Once you try to mix it at very high speed, once you try to open the tap and water starts mixing inside the bucket, easily the bubble formation will be there. Sometimes it may fly if it is very low weight, or sometimes inside that bucket or the container itself, it will try to form the bubbles and burst out. So this is the phenomenon. In that case, we are taking the surface tension. Okay, surface tension is trying to keep the molecules inside this spherical body or the hemispherical body from the inside also, from the outside also. And pressure is also acting from the air inside, also from the air outside. Or for the soap bubbles, if you take, we can assume one layer of water, one layer of the soap. So like that, why we have considered two surfaces or the two line of contact? Because the two forces are acting, one from the inside, one from the outside. Or pressure required is also double, two times, because pressure is required from the inside to burst out. Outside pressure also should be kept constant so that it can burst out. I hope the point is clear. That's why we are taking the tensile force 2 sigma, or else you can take the pressure two times. Any one side you can take the two times force, not both side. So as concept is required, we are taking surface tension two times because it is having the two parts of the forces. Okay. So again the same equation for the hemispherical or the cut portion of the hollow bubble. If you take the force required to overcome the spherical bubble to burst out, I can balance these two equations of pressure on one side and surface tension on the other side. So always pressure if you take, or the force on one side if you take, that is P is in contact with the pi by 4 d square or the surface area or the projected area. In this example you can see sigma, it is two times bubble, two layers are formed, or the two forces are acting inside and outside. So 2 sigma we are taking. Projected area, if you see, it is again a circular surface. So that circular surface is nothing but projected area pi by 4 d square. And for the surface tension, the line of contact for the surface tension, it is acting on only the rings. That is pi d, or you can write 2 times pi d. So on these rings, two tensile forces are acting. So pressure required to overcome that tensile force is equal to 4 into 2, 8 times sigma divided by d. Have understood the bubble concept? What is the tensile force, how it is proportional and inversely proportional with respect to sigma and diameter? Okay. Then one more topic is surface tension with respect to cylindrical objects or the liquid in the form of cylindrical flow. Here also we have taken half cylindrical liquid. We can assume before dividing into half, earlier it was completely filled in pipe, or it is stored in the well. As you've taken the example well, it is in the well in a cylindrical form. So the force required to separate this cylindrical molecules. So what is the line of contact here? You see the tensile force is acting on this length, on this length, diameter T, again throughout the height L, and again here D. Okay, pressure. So pressure we are taking the projected area. What is the area of this projected part where the tensile forces are acting? Because tensile forces I am talking only when the contacting liquid. So it is in contact with the liquid only on this area, not on the other area. Other area was connected with the pipe surface, or it is connected with the surface of that well in which the water is stored. Okay, so that area we are not focusing. We are focusing the area which is earlier in contact with the same liquid or same material. So that if I consider area that is in the form of rectangular in shape, I think all of you agree. That rectangular length area if I take, it is d into L, diameter into length into P, and this sigma if I consider, it is acting more on the vertical lines, less on the diameter, because diameter we can assume it is very small. So to keep the relation as inversely proportional to pressure and diameter, we are considering this length of action for the cylindrical objects, the length in contact or the length on which the surface tension is acting is more compared to the diametrical side here, D side. So I can write it as sigma into 2L, 2 times length. After substitution, I can write it as P equal to 2 into sigma by D. If you take 2 into LD, what will happen? The D and D will get cancelled. I can write it as P equal to 2 into sigma. That is also fine. But what will happen? Diameter is negligible in this form. But the projected area is what? Complete area on which the pressure is required to be applied to overcome the surface tension will be considered with the surface area. But for the surface tension, we can consider only the line of contact. So line of contact for a given length of cylinder, if you take huge length, the diameter can be neglected. Or this pressure and diameter relation, in this diameter may be very small. Okay. So that in the color it is shown like this. Yes, here. So here if you see, force equal to what? Sigma into D into L. That's on one side. That is written here. Sigma into 2L. Other side is P into DL. Projected area into pressure. Surface tension, it is more on length side for the cylindrical objects. So they have taken only 2L. So P can be written as 2 sigma by D, which is can be compared easily with these equations. 8 sigma by D, 4 sigma by D. Now we can remember for droplet, what is the equation? For hollow bubble, it is twice the droplet, 8 sigma by D. For liquid jet or the cylindrical water volume, we need the pressure or the minimum pressure of 2 sigma by D to separate them apart. Now comparing the surface tension, so one of the relation is as temperature increases, the surface tension of the liquids increases. This you can see in boiling milk. So as the milk boiling increases, the surface tension or the layer of the what is that milk, you can just observe how the layer is formed and it will come up as the temperature rises. Okay, and also there will be less effect with the pressure, but what will happen as the pressure increases at these points, the surface tension can be cut off or the removed, so that you have to overcome minimum pressure. But change in pressure will be having some effect, little effect will be there. We will take one simple example to understand these concepts. So just observe here. So one question is given here. What is the pressure inside droplet of water of 0.05 mm? See now the word droplet, once it is written, you read the equation. What is that equation? P equal to 4 sigma by D, because they are asking the droplet and some pressure. So relate the droplet equation or the droplet concept with the pressure, that is P equal to 4 sigma by D. Now we need to find out what is the pressure inside acting of droplet of 0.05 mm, that is the diameter, at 20 degrees centigrade. So can you tell me the temperature is it affecting in the problem as per our formula is concerned? Because temperature is not there in the formula itself, so it is not affecting much. And also, if you see, if the pressure outside the droplet is 103 kilopascal, take sigma equal to 0.0736 Newton per meter at same temperature 20 degrees centigrade. Means this experiment is conducted at the same temperature, so there is no need to take different temperatures consideration, as well as in the droplet equation, which is relating with respect to surface tension and the pressure, there is no a term called temperature. So temperature is not related. Just to confuse you or to just to understand whether the experiment is done in different temperatures or in the same temperature, they have told it 20 degrees centigrade. Okay, this is one thing. Next is the inside pressure or the outside pressure, whatever it is. What they are asking, what is the pressure inside? Only inside pressure we want to check. That is the pressure with respect to molecules of the water, how much it is acting. If we overcome that pressure, I can divide again the droplet into two halves, hemispherical pressure or the droplet by that external pressure. Now, if the pressure outside the droplet is 103 kilopascal, take sigma. So, by these given values, one should find out what is the inside pressure of the droplet. Now, for this, I can take one of the relation, pressure inside minus pressure outside, or the difference of pressure is the required pressure to overcome the surface tension of the droplet. Okay, means what I am considering is, consider this, to overcome that spherical droplet, I will apply some pressure so that that droplet can overcome, or I can overcome the surface tension, and I can pierce some, or I can cut that spherical droplet into two halves, or I can pass a plate of thickness, very negligible thickness, and I can shear it off. So how much pressure is required to break it out? So that pressure P I can consider P inside minus P outside, or just difference of the two pressures. So what will be the pressure now? P inside and P outside. Outside they have given 103 kilopascal. Inside pressure, how you are finding? P inside is how much? P plus P outside. What is that P? Pressure equal to, cut that into half, or to overcome the surface tension. That P can be found out from the above equation, 4 sigma by D for the droplet. So find the P value. P outside value is given, and inside how much is the pressure built by the molecules of the water, so that one can understand whether the cohesive force is more or the pressure required to separate them is more. That is important. It's 145. Okay. So just this P, the pressure what is applied, okay, by this formula, if you see, the pressure required to overcome the tensile force is 5.88, or to keep it in balance is 5.888 into 10 raised to 3 Newton per meter square. Okay. And P inside, if I find out with outside pressure of atmospheric pressure, it is coming around 108.88 into 10 raised to 3 Pascal, nothing but Newton per meter square. Now, can you comment me whether the inside pressure is more or the pressure required to pierce it out is more? So pressure inside is more. Means here we are trying to just observe not with the pressure between the molecules. Pressure between the molecules is 108.88 into 10 raised to 3 Pascal. What we are focusing, if you focus on the pressure required or the difference of pressure what is available, due to which the piercing is possible. So only the pressure difference, if you maintain around 6 kilonewton per meter square or 6 Pascal, we can easily separate the droplet into two halves. Okay. So I think the point is clear to everyone. Here he is asking the pressure required or the minimum pressure to keep the droplet as it is 6 kilonewton per meter square. To overcome it, I have to just cross 6 kilonewton per meter square. Okay. So only due to this difference in pressure, the droplet can be cut into two halves. Okay, next class we'll consider some more examples and we'll move to the next properties. Okay, thank you. Okay.